Okay, so now it's time to prove the second part, where the d's appear. This is the we define it as the operator ds as mu square minus multiplication s over 2. We will use that. Okay, so we will start just like we did with the first part, just making triangular inequality using triangular inequality. Okay, d1 1/2 e minus mu x x u squared minus b squared u plus b norm 2 plus d 1/2 e minus mu x x, and I will have the same but with the sum u squared plus b squared, and now it will be the same with a minus. Okay, so now we're going to use the generalized Leibniz rule to bound as the same way we did with Helder, but now taking account the operator ds f g, you can be bounded considering s alpha and beta pi q I p going to be bounded as ds plus alpha f in p1 multiplied by d minus alpha g in q1 d minus beta f p2 ds plus beta g q2. So if we use this with s 1/2 alpha equal to 0, beta equal to 0, and PIQI the same way we used in the Helder in the first part, we will have that d 1/2 fg norm 2 is going to be equal to this in norm 6 g in 3 f infinity d g2. Okay, so let's use that. It will be less than equal within a constant to d 1/2 e minus mu x x convolution u squared plus b squared u minus b, this is a minus, okay, and this is a plus. This will be norm 6 u plus b norm 3 plus, now we have again e minus mu x x convolution u squared minus b squared, now it's norm infinity, and now we have d 1/2 u plus b 2, and now the other term we have to bound in the same way, d 1/2 e mu minus mu x x u squared plus b squared 6 u minus b third plus e minus mu x x convolution u squared plus b squared norm infinity, and once again d1 half, now u minus b. Okay, so now we want to bound this one, for example. This time it has a d1 half, so we want to bound d1 half e minus mu xx convolution u squared minus b squared norm 6. Okay, so if we want to bound it, we have to recall that d to the minus alpha is mu squared minus inflation minus alpha over 2, considering alpha between 0 and 3, mu positive greater or equal than 0. And we know that what d makes is takes f to the convolution of g mu alpha, where g mu alpha is a kernel, is similar to the Bessel kernel, only that we're considering this mu. This mu, it can be represented here by the exponential of e, and the alpha will be an exponential in the absolute value of x. So if I have d of, let's say, s of f, then this can be represented by, let's say, g mu. Well, in this case, if we put minus s, then we would have s here and convolution f. This had to be positive. In the case of this term, we have e minus mu x absolute value of x. That means that in this case alpha is equal to 2. So it's like applying d2. So we have d1 half and d2 of a function. This could be all f. So we will have d like applying here d2 minus 2, because here it was okay. Or we can put minus here. We'll have that change. So we will have here, after applying 2 times d to this function, don't forget that this was within a constant here, so this will be less than equal within a constant to, well, if we apply d minus 2 and then 1 half, d minus 3 half u squared minus b squared norm 6. Okay, so we can transform now this again into kernel notation. That would be norm of g mu 3.5 convolution u squared minus b squared norm 6. Okay, so it's important now to notice that the kernel g mu alpha is in a weak of 3 multiplied by 3 minus alpha in R3, and this can be proven because you can bound g mu alpha by g0 alpha, that is a function that has a constant over the absolute value of x 3 minus alpha. Okay, so it is bounded by a function that is in L weak. So if g mu alpha is in L weak, then we can use it to bound the norm with the weak Young's inequality. So recall with Young inequality we have a convolution, and choosing R, Q, W, and P such that satisfies this, we can bound with G mu alpha, the kernel. So we can do it here, and we will obtain, in this case, G mu 3 half 2W, and we will have, well, then the other term, U minus B squared, and we will have 3 halves here. Okay, so as we did before, we take this as a constant, we divide this and make Helder, and we will obtain U plus B norm 3, U minus B norm 3. So we've bound this one, and now we're going to try to bound this one we have here. Okay, so this term we can bound it. Well, first mu is positive, so we can bound this by 1 over x convolution mu u squared minus b squared norm infinity. Okay, so this is a convolution, so we can bound this by, well, norm infinity supremum y in R3 of the value of the integral in R3 of, let's say, ux squared minus bx squared over x minus y dx absolute value. If we split up this, we will have now the supremum y in R3 of the absolute value of the scalar product of ux plus bx 1 over x minus y ux minus bx. Okay, this can also be written as supreme y R3 of ux plus bx over x minus y 1/2 ux minus bx x minus y 1/2. Okay, so we can bound this by Cauchy-Schwarz inequality, and we will have that integral R3 of ux plus bx squared x minus y 1/2, and then we will have the same, but instead of plus we will have minus. Okay, squared x minus y 1/2. Okay, in the same way we did in the first part, we can bound this by minus Laplacian 1/4 u plus b 2 and 1/4 u minus b 2. So again, as we did in the first part, we can bound this by u plus b in h1/2 and u minus b h1/2, and this will be less than equal than u1/2 plus b 1/2 multiplied by u minus b. Okay, having bound this term. So we bound this one and we bound this one. So the others that are left are all bounded in the same similar way. Just here we have a plus. Here is the same with a plus. So all we will have the result, the Lipschitz result, just following the same things we did to bound this one and this one. Okay, we just have to fill in the detail. For example, here when we got here, we can use that the norm u in 3 is less than equal than norm u in h1/2 to bound this part. Okay, we just have to fill in the gaps with what we just all we can.